Alright, calculus students, as promised, I'm going to be doing 2 problems from the Reimann Sum package you guys have with. It also has some intermediate value theorem, extreme value theorem, and mean value theorem kind of mixed in. So we're going to start by looking at the 2007 number 3 here, which gives us this table of values that we're going to be using a lot of in the future, so keep that in mind. And it says the functions f and g are differentiable for all real numbers, and g is strictly increasing. That might become important. The table above gives values of the functions and their first orders as selected values of x. The function h is given by this function. So h of x is f of g of x minus 6. So in part A, it says explain why there must be a value r for 1 is less than r is less than 3, such that h of r is equal to negative 5. So what we're going to do is we're going to show that h of 1 and h of 3, we're going to figure out what those are, and basically if those two numbers are around negative 5, so if one's bigger and one's smaller, you have to hit negative 5 to connect those 2 points. So I'll explain that more in a second, but basically if we have points at 1 and 3, and then if we have y values that somehow go through negative 5, then we have to hit negative 5 somewhere in there. So what I'm going to do first is I'm going to find h of 1. So just plug into that function, so f of g of 1 equals minus 6. And just figure out what those values are from the table. So g of 1 from the table is 2, so we get f of 2 minus 6, and then f of 2 is 9, so we get 9 minus 6, which is 3. Do the same thing for h of 3. So you get f of g of 3 minus 6, which is f of g of 3 is 4, so you get f of 4 minus 6. F of 4 is negative 1, so negative 1 minus 6 is negative 7. So sure enough, in between these two values is the number negative 5. So we would just say, as our justification part of this, that there must be a value r for where r is between 1 and 3, such that h of r is equal to negative 5, since h of 1 is equal to 3, and h of 3 is equal to negative 7, and the function h must have passed through h of r equals negative 5, since h is continuous. And where this is actually coming from is this is actually coming from the the intermediate value theorem. An intermediate value theorem just says if you're continuous and you're connecting these 2 points with a function that's continuous, you must go through that negative 5 at some point. You have to. You can't be skipping over values because then it would be discontinuous. So that's part A. Part B says explain why there must be a value c such that the derivative is equal to negative 5 at that x equals c. So what we're going to do here is we're going to find the slope of the secant line. So we're going to find the average rate of change between the 1 and the 3. So we're just going to take our slope between 3 and 1. So h of 3 minus h of 1 all over 3 minus 1. Well, isn't it nice that we just found those? So negative 7 minus 3 all over 2, you get negative 10 over 2, which is negative 5. So basically, we're saying that since the average rate of change is negative 5, there has to be an instantaneous rate of change, that's the derivative, that's equal to negative 5 at some point too. And that comes from the mean value theorem. So we would just say for our justification that there must be a value c for 1 is less than c is less than 3 such that h prime of c is equal to negative 5, since the average value, or the average rate of change, between x is 1 and x is 3 is negative 5. And h is differentiable and continuous. And again, this comes from the mean value theorem. Okay, so if you want to look that up, that's something you might want to look into. Now in part C, you could have done part C without even touching A and B. And again, guys, make sure you're using good test-taking strategies. For part C, it says let W be the function given by W of x equals the integral from 1 to g of x of f of t dt. Find the value of W prime of 3. So we need to find W prime of x first. So that's going to be the fundamental theorem of calculus. When we take the derivative of an integral, we get the original function back out, but with that g of x plugged in for t, and then don't forget to multiply by the derivative of what you just plugged in. Okay, that's the whole chain rule. If I'm going to plug something in for a function, I need to make sure I multiply by the derivative. So if we're trying to find w prime of 3, we're going to take f of g of 3 times g prime of 3. Again, we're going to go to our table. G of 3 is 4, so we have f of 4 times g prime of 3 is 2. F of 4 is negative 1, so we have negative 1 times 2, which is negative 2. And that's all you had to do in that problem. So again, that's from the fundamental theorem of calculus, that if I take the derivative of an integral, it's that function with that top value plugged in, but again, times its derivative. So and finally, for part D, this is that whole inverse rule that we talked about before. It says if g inverse is the inverse of g, write an equation for the line tangent to the graph of y equals g inverse at x equals 2. So here's what I'm going to do. I'm going to call f of x. I'm going to make that be our g inverse of x. And then again, what I need to do here is I need to get rid of that inverse. So I'm going to take g of both sides. So we have g of f of x is equal to just x. And you know, I should probably use something other than f. Sorry guys, let's call it h of x, just because we don't want to use the same function that we had before. And not even h of x, because h of x was used. So I don't know, let's call it salar of x, so s of x. Okay, so now we have g of s of x is equal to x. So now we're going to take the derivative of both sides. This side we've used chain rule, so g prime of s times the derivative of s, so s prime of x, is equal to the derivative of x is 1. We're trying to find s prime of x because we're trying to find the derivative of g inverse. So we're going to solve for s prime of x is equal to 1 over g prime of s of x. And what we're trying to do is we're trying to find s prime of 2. So 1 over g prime of s of 2. Now here's where it starts to get a little tricky because we have to figure out what s of 2 is. S of 2 is equal to g inverse of 2. Which g inverse of 2 is going to be the same as, well, we have to look at when is g equal to 2. And that's when g is 1. So g inverse of 2 is equal to 1. And I got this from the table. The only time we got the y value equal to 2, because that's the same as the x value over here, is when the x value is 1. So now we just found what g inverse of 2 is, which is our s of 2. So we get 1 over g prime of 1, which g prime of 1 is 5 from the graph. So 1 over 5, and you got your solution. Okay, and that's a tricky question. Okay, I'm sure a lot of people miss that one because it's a very obscure rule. Now let's take a look at the next question you guys have. And actually, I want to go over the 2010. Just because it's a little bit of a different problem, and it's one that requires you really knowing your Reimann sums very well. So it says, we have this table again given to us, so tables seem to be a big thing here. And it says, a zoo sponsored a one-day contest to name a new baby elephant. Zoo visitors deposit entries in a special box between noon and 8 p.m. The number of entries in the box t hours after noon is modeled by the differentiable function e for 0 to 8. Values of e of t in hundreds of entries, keep that in mind, at various time t's are shown in the table above. Alright, so in part A, it says the data, use the data in the table to approximate the rate in hundreds of entries per hour at which entries were being deposited at time equals 6. So usually we'd take the derivative, but we don't have the derivative. We can't take the derivative function. So what we're going to do is we're going to take the points surrounding 6, which are those two, and then just do an average rate of change, okay, to estimate that derivative. So if we're trying to estimate e prime of 6, we're going to use average rate of change. So we're going to take e of 7 minus e of 5 all over 7 minus 5. So e of 7 is 21 minus e of 5 is 13 all over 2. You get 8 over 2, which is 4. So it's going to be 400 entries per hour is our average rate of change. And again, that's going to approximate the instantaneous rate of change. In part B, it says use a trapezoidal sum with the 4 subintervals given by the table to approximate the value of 1 over 8, the integral from 0 to 8 of e of t dt. Okay, so do a trapezoidal sum. First of all, leave that 1/8 out front, times, for a trapezoid, it's always going to be 1/2, but times the height. Now we're going to, this 1/2 is going to be attached to every single trapezoid. So we can kind of factor it out, because it's going to be 1/2 height times something, 1/2 height times something. So let's just factor it out. Now the height of the first trapezoid, let's go back up, is 2. Okay, that's our height. So it's going to be 2 times base 1 plus base 2. So it's going to be 2 times 0 plus 4, plus our next trapezoid has a height of 3, times this will be base 1, this will be base 2. So it'll be 3 times 4 plus 13. And you're going to follow that same pattern. So the next set of trapezoid is going to have a height of 2, times the base 1's 13, times the base 1's 21. Plus, then the last guy has a height of 1, times 21 plus 23. Okay, at this point, this is where your calculator comes in. You get 1 over 16 out front when you multiply those two, and you get 171 when you add up all these numbers. And so when you divide that, you get 10.688 when you round it, and again, that's approximation. And this will be hundreds of entries. Okay. Now what this is giving us, this formula here is the average value formula. So what this is giving us is it gives the average number of entries in hundreds from time equals 0 to time equals 8 hours. Okay, so that gives us an average. All right, now in part C, this wants us to find at 8 p.m. volunteers begin to process the entries. They process the entries at a rate modeled by the function P, which they give you that function, hundreds of entries per hour for A to 12. According to the model, how many entries had not yet been processed by midnight? So what I'm going to do is I'm going to find out how many had been processed. So I'm going to take the integral from 8 to 12 of P of T dt. And I'm just going to completely plug that in my calculator. And when I do, it turns out pretty nice. You get 1,600 entries. And just keep in mind that's the number that have been processed. So how are we going to figure out how many have not been processed? Well, we're going to go to how many were entered at time equals 8, the last time people could enter, which was 23. And that was how many total entries there were. So we're going to take the 23 total entries and subtract 16, and we get 7. So 700 entries had not been processed as of midnight. So they got quite a bit of work yet to do on that problem. Okay. And then finally in part D, it says, according to the model from part C, at what time were the entries being processed most quickly? Now this is a max question, so we're trying to find when is it moving the quickest. So what we're going to do is we're going to take P prime of T, and this is something you should take the derivative of on your own, so you get 3t squared minus 60t plus 298. And we're trying to find critical points. So we're going to set this equal to 0 and plot that into our calculator and find when that's equal to 0. Okay, so let's go into our calculator and do that. So go into your y equals, and clear all this garbage out. And we have 3x squared minus 60x plus 298. I'm going to change my window. We want to make sure we're looking only between 8 and 12 because that's the time they were processing. And I can probably just go between negative 10 and 10 because I want to make sure I see negative derivatives and positive derivatives. So let's graph it. Now remember these are positive and negative derivatives. So this is a positive derivative. We have negative, we have positive. We're trying to find a max. It's going to occur where you go from positive to negative or at an endpoint. So we also have to consider the endpoints as well, which as we're increasing, this over here could be a max as well. So we have potential max at time as, let's figure out where that from positive negative where this point is. So second trace, 0. Let's figure out where that point is. And one of the possible maxes is 9.184. And the other possible max is that right endpoints are increasing up to that point. You need to test both of those. So when I plug in 9.184 into the original function, I get that I'm processing at a rate of 5.089. And then if I plug that into 12 into it, I get 8. So comparing those two, this is the bigger one. So we would say that entries are being processed most quickly at time equals 12 hours. And again, you had to test both of those because those both were maxes. The one was a critical point max, one was an endpoint max, and sure enough, the endpoint max was bigger. So make sure you're testing all possible maxes when you're doing these. That's it, guys. You have the other two problems in the packet that aren't done for you, the 2009 is your homework, the other one is extra practice. Make sure you try that extra practice. You never know what's going to show up on the quiz.